Hello everyone, I'm Jiaqi Gao, a fourth-year PhD student at Harvard University. Today I'm going to show you what does instant routing look like in the data center and how to improve the diagnosis process through domain-customized instant routing. This is a joint work with the University of Pennsylvania, Microsoft Research, and Microsoft. Availability and maintaining service-level objectives are the biggest challenges facing cloud operators today. Operators are working hard day and night to keep the complicated system up and running. However, incidents can and do happen. Here is a table that collects the public incidents of the past 6 months in the Google Cloud and Azure. We can see that Google Cloud reports 69 incidents and Azure reports 21 incidents. It takes both clouds hours to resolve these incidents. Note that these are just public incidents. There are way more incidents under the cover. Now let's see the life cycle of an incident. Firstly, when the monitoring systems deployed in the data center detects the abnormal behavior or the customer is experiencing issues, an incident is created. The next step is finding the failing component, which equals to finding which team is responsible for the incident. This process is usually done by asking each team whether the problem belongs to its components. If so, then the team takes over the incident and apply the corresponding troubleshooting procedures. If not, then we need to find the next team until one team claims the incident. Just like when we debug a buggy software, rather than fixing the bug itself, we often spend most of the time finding where the bug exists. From our measurement, finding the right team is time wasting. Here is a CDF curve of the normalized investigation time when one or multiple teams investigate the incident. We can see that in the median, misrouted incidents takes 10 times longer to resolve compared with the incidents that were sent directly to the responsible team. So how to reduce misrouting? Previously, people tried to solve this problem with two approaches. Firstly, they build application-specific diagnosis systems, such as NetPro, which trains on each application, and DeepView, Sherlock, which explicitly encodes the application dependencies. But because there are too many applications in the data center, we cannot build one diagnosis system for each application. Another line of work tries to route incidents based on instant text description, such as a global instant routing system running in Azure, which is built on top of the NSA 13's work, NetC. But because it fails to consider the domain knowledge in each team, the accuracy is not high. Let's revisit our instant routing problem. We want to build an instant routing system that when an incident happens, it can summarize the engineer's domain knowledge and other resources, such as the monitoring data, and sends the incident to the correct team. Our first idea may be build a principled algorithm based on well-known rules and conditions over the set of inputs, but this can be extremely difficult given the multitude of teams, the magnitude of the data, and the diverse nature of the problems that occur in practice. Then another approach is machine learning. We can let a machine learning algorithm learn a pattern. There are many ways to build such a machine learning system. The simple solution would be build a huge machine learning algorithm that solves the problem at once. But we quickly found out that it is really hard to build such a single monolithic instant routing system with high accuracy. There are 4 problems. The first problem is the curse of dimensionality. Because the global routing system should consider everything, this large amount of information can easily result in a huge feature vector, but we don't have enough examples to train it. The second problem is uneven instrumentation. A subset of teams will always have gaps in monitoring, either because the team has introduced new components and analytics have not caught up, or simply monitoring is just hard. The third problem is the input is constantly changing. We may constantly experience stale components and monitors. The fourth problem is limited visibility. Because we're sitting at a global position, it is difficult to understand the appropriate feature sets from each and every team. So here we present Scout, a team-specialized gatekeeper. Instead of sitting at a global position, the per-team-based Scout simply answers the question, is my team responsible for the incident? So when an incident is created, the Scout can run local checks and intercepts or reject the incident based on the result. This design has 3 advantages. Firstly, each team only needs to maintain 1 Scout, so this solution is realistic and applicable. Secondly, our per-team-based Scout can easily leverage the team's domain knowledge, such as what are the team's responsible components, what are the monitoring systems deployed in the data center. Thirdly, each team can evolve its own Scout independently without affecting other team Scouts. To build such a Scout, we found there are three challenges. As we said previously, the Scout should leverage the monitoring data available. But since there are millions of devices in Azure, the amount of related monitoring data is huge. How to process them? Our insight is the incident itself can guide the investigation. The incident description usually can tell us the candidates of the affected devices, such as the affected servers, switches, and clusters. We can leverage the operator's domain knowledge and encode the device's naming convention through regular expressions and extract the potential devices out. After this step, we can find related devices monitoring data. Through this method, we can shrink our scope and collect a reasonable amount of monitoring data. Then, the next challenge is how to create a fixed-length feature vector out of the monitoring data. Each incident may have variable number of devices. The monitoring data also has mixed types. Some of them are time series, such as the temperature data. Some of them are event-based, such as the reboot event. How to summarize them together? Here, we propose a two-tier aggregation solution. In the device tier, for the time series monitoring data, we normalize the data and compute a series of statistics, such as different percentiles, average of the data, etc. For the event-based monitoring data, we sum the number of events during the incident period. After getting each device's feature vector, we summarize them via statistics such as percentiles and averages. So through this algorithm, we can build a fixed-length feature vector for each incident. After collecting the feature vector, the third challenge is which computation engine do we use? The solution we chose is a hybrid of a supervised learning algorithm and a statistical algorithm. For the supervised learning algorithm, we use the random forest algorithm. It learns based on the historical incidents and related monitoring data and has high accuracy on old or recurring incidents. Another benefit of the random forest algorithm is that it is interpretable. We can provide more insights to the engineer rather than just say yes or no. But because this algorithm is trained on top of historical incidents, it has low accuracy on new or rare incidents. So we use the change point detection algorithm to overcome this drawback. In a nutshell, the change point detection algorithm is able to detect the change points in a time series of monitoring data, and we believe these change points might be the cause of an incident. So then how to merge these two algorithms together? As we said previously, if the incident is recurring or common, then the random forest algorithm has high accuracy. So we can let the incident itself tell whether it is a new or old incident. The selector uses a meta-learning to identify new incidents. If the selector thinks it is a recurring incident, it will send the incident to the random forest model. Otherwise, it will call the change point detection algorithm. So at last, we can call the corresponding computation engine and get the classification result. Okay, so now let's revisit the overall design of a Scout. Given the incident description, the Scout uses the domain knowledge to collect the devices and find the related monitoring data. Next, the Scout builds a feature vector and assigns to the hybrid computation engine and returns a classification result. To evaluate the Scout's performance, we build a Scout for the physical networking team, which is in charge of each and every switch and router in Azure. We collected 9 months of incidents and randomly split them into training and testing set. For the baseline, we compare the Scout against the current incident routing system without Scout's involvement. The current incident routing system includes the engineer's runbooks, past experiences, and the NLP system we introduced previously. Here is a table showing the overall performance metrics, precision, recall, and F1 score. The baseline can achieve around 90% of precision and recall, and here is a result of a Scout. Compared with the baseline, the Scout can gain 10.3% on the precision and 5.8% on the recall. This 10% gain saves more than 20% of the total investigation time in 40% of the positive incidents. Due to the time limitation, there are a number of things we did not talk about. The first thing is the investigation of why incidents are misrouted. We also did not mention the design and evaluation of a Scout master that combines multiple Scouts and summarizes their results together. We also didn't talk about the series of extended evaluations. At last, we also wrote down the lessons we've learned from the deployment. Please check our paper for more detail. So, in conclusion, we show that incident misrouting is the main challenge for maintaining service-level objectives in the cloud. And we propose the Scout, a distributed team-specialized gatekeeper. We built and deployed a final Scout that can achieve higher than 97% precision and recall. Thanks for listening, and I'm happy to take questions.
Okay, thank you so much, Jackie. The first question is from Chuan. The question is, could you elaborate a bit on what type of components or devices you collect data on?
Hi. So because we are building a Scout for the finance team, actually, since the finance team is in charge of each and every switch and router in the data center, so the first type of device is the switches. And because the switches are connected to the servers, we also need the server information, such as the ping data, to help debugging whether networking is a problem or not. And third type of device is because sometimes the incidents only mention that a cluster is not functioning. So we also need to take into consider the whole cluster's information. So those are the three types of devices we collect information on. And I would just want to note that because different teams may have their own special components. For example, SLB may have their software components, or the end host team may have their NICs. So different teams may have different components. Yeah.
Thank you. This is very interesting. The second question is from Enan. The question is, did you ever find a wrong responsible team? If that was the case, do you mind sharing the scenario with us?
Yeah, so we do have a lot of, we do find some false positives in our, both false positive and false negatives in our evaluation. So the false positive, actually, there are two categories. So for one of them is we actually missed some kind of monitoring data. So one specific example I can give is we are missing the DHCP information from the switch, and the server is complaining that it cannot grab the IP. So we are actually not collecting the DHCP information previously. So those kind of incidents, we just see that everything is good, right? The switch is good, server is good, but it just cannot get the IP. So those are kind of one false positives and false negatives. For the false positives, I can give another example of concurrent incidents. So for example, one incident is triggering one problem is triggering multiple incidents in different teams. So then it's like the finance team do have the problem. It did say the problem, but I think the root cause is not in that specific team. So I think in this case, actually we need is for a global routing system, as we said, we cover in the paper, like how to summarize the result from multiple scouts and try to reduce this type of false alarm. Yeah.
This is very interesting. Just to maybe a quick comment about the final question, I want to ask you, in the paper, there's a very nice discussion about when not to rely on scouts.
Yeah.
And I'm wondering if you can elaborate a little bit on that.
Yeah, so when not to rely on scouts, so one of the examples is not to use scouts on pretty obvious incidents. So those are like two types of problems. So first is in the reality perspective, actually those are not incidents that is causing troubles. So usually those incidents are sent directly to the responsible team, and actually those are the incidents that like we will have really marginal gains. And the second type is, and the second reason is when those, because scouts can sometimes do make mistakes. And from the this is more on a person's like perspective, like when the engineers trying to use your system, and when they say that, oh, like your system make mistakes on really simple incidents, they lose faith in your performance, right? So those kind of incidents, like we cannot, the gain is small and our loss of making mistakes is pretty huge. So I think in production, we try not to turn on our system in such cases. Yeah.
Thanks so much for your talk, Joshi. I think some questions are coming, but perhaps we can start with the following. So you built a Scout for the physical networking team, and you said potentially you can also build for other domain, for example, storage. How easy is actually, so once you create for one domain, to create for a different one? Is a similar process, or you anticipate any challenges, for example, as you are going to build one for storage, let's say?
Good question. So actually, when we were submitting the paper, actually, we only built the Scout for finance team. And after the submission, we try to embrace other teams. So one of the things that, so theoretically, so in our design, there are only one thing that the operator needs to provide, which is how to extract their entities from the instance text. For example, like definitely because, so give an example of SLB team, they definitely have different naming schemes for their own devices, such as SLB nodes, for example, they have hubs, etc. So they need to provide that information. Another information they need to provide is how to link the monitoring data with the entities. So different teams perhaps they use different systems to collect monitoring data, or they have different access requirement for collecting monitoring data. So those are the two things theoretically need to build a Scout. But in reality, we found that there are more things than we need to do, because first of all, there's some data connectors that are specific to the team. So we need to build specific wrappers so that we can collect the monitoring data. And secondly, there are some, I think, so because I am not fully, after the submission, I'm not required to touch the data. So this is second-handed information. So I think probably there need to, a little bit tweaking, so need to add more domain knowledge rather than just the devices information. For example, if you have a SLB team that is depends on the finance team to provide the functionality, they need to encode this kind of dependency information somewhat in a somewhat sense to make it more robust, rather than firing false alarms when the finance team actually affecting SLB teams, and actually it's not SLB team's fault. So when this kind of complicated dependencies come in, we need a little bit more mechanisms to make it higher accuracy.
Interesting. Thanks a lot, Josh. It's very interesting. There is another question that arrived on Slack, and this is from Anna that is asking, do you mind to show any concrete example in Microsoft, the one that you can share, of course, publicly? Before a Scout was proposed, a teamwork problem happened, but after Scout was built, this problem was fixed.
Oh, actually, we do have an example in the 20-minute video, because like that is really long, that incident, the teams bouncing between many teams actually. So we do have a similar example that, we do provide, I think we provide 2 incidents in the paper, actually 2 case studies in the paper saying that, explaining what are the difficulties, or what does the incident look like, why the incident misrouted, and actually we are correct on both. So I don't want to read the paper, but please check the paper for it.
Okay, yeah. Okay. Thanks so much. And then the last question from Wei that was asking if Scout is resilient to cheating. And for example, say if someone can reassign the blame to another person by cheating your system.
I think because I think this is more on the labeling, right? So because if you label, if you feed into the wrong label, definitely the system can be cheated. But I think the problem is in reality, no one wants to cheat on the incident, right? Because the engineers are facing the customer actually. They don't care about who solves the incident. Actually, they care about whether the customer is satisfied with the performance of the system. So I think when the goal is set, I don't think there is a goal. There is not any, what is the word? But they don't want to. I would say that they don't want to cheat the system.
There is no incentive to game the system.
Yes, yeah, exactly.
Yes.
Yeah.